Hi, everybody. Welcome to class today. I have on the screen um, this question. It's similar to what we looked at yesterday. Yesterday, we had a circle, small circle rolling on the outside of a bigger circle. So what changes when instead the circle is now rolling inside the big circle? So my first question to you is just to think about this for a minute. What do you think the curve will look like? This small circle is going to be moving counterclockwise. At least the center of the circle is going to be moving counterclockwise. So just take a minute to think about, there's a couple of feasible options. What are they? Okay, the comment that I see is that pedals will be on the inside. Let's take a look here. Here is the actual scenario. Hmm. So if I come here and say rolling hypocycloid, and if I move the slider, first thing to kind of notice is that unlike yesterday, when the circle was outside, the small circle was rolling outside the big circle, in order for this circle to roll, uh, in order for the circle to move counterclockwise, look at the points on the circle. It's actually going clockwise. So that's kind of interesting already. Yesterday, they were both going counterclockwise when it was outside the circle, but you can see that the way a circle would actually roll, that point would go clockwise. So we basically end up with like a cycloid-looking thing like that. And it is like a petal of the flower. Now this one creates the second petal, the third, but they're inward facing. Today we're going to find out what the equation of this is. This shape is called a hypocycloid. But we're going to build up to it with another question. And really, we only have three questions for today. Just like yesterday, I'm going to distinguish between whether a circle is rolling or floating. So my first scenario, I have a circle, and it's inside, the small circle's inside the bigger circle, but it's not rolling, it's floating. And that's going to cause, that's actually going to be easier to analyze. So this circle here is kind of floating around. And when you're floating, you have to be told also what the rate of revolution is, like how for every degree that it revolves, for every 1 degree it revolves, how many degrees does it rotate? Also, you have to be told not just whether the circle is moving counterclockwise, but you also have to be told about whether or not the points on the circle, because if it's floating, there's no physics that it needs to adhere to. It could be floating counterclockwise while rotating clockwise. Well, Jonah asked about what's the difference. So when it's floating, it's not really, it's like in the air. So there's no constraints about like how fast it spins. It could be spinning really fast while it revolves slowly. But when it's actually rolling, kind of like gears, it's going to roll. It rolls at a certain proportion, or the number of rotations is related to each revolution by like the physics of it. I think if we put gears on it, like you see in a spirograph, it would make more sense. Why rolling, you really can't control how fast the spinning happens. It's going to spin as fast as it's going to spin. Now, as far as the equations go, the floating is easier to understand. Here's a picture of the floating scenario. So I come back here and I bring up, and all these, you have access to all these floating hypocycloid. It's not technically a hypocycloid if it's floating, but it gets the idea. So here I actually put in the R value is 5, meaning that for every 1 revolution, for every 1 revolution, it's going to do 5 rotations. And we can see one thing about this is that it's revolving counterclockwise, and the point on it, because it's just told to you, is going counterclockwise also. So it almost looks funny if you take a look. It doesn't look like something looks weird about the rolling, like that point seems to be going like backwards from what it would actually do. But when you're floating, you have the flexibility. You can float and rotate one way or the other way. We're not constrained. So we get a picture that looks like this. Now, this is very, very similar to what we did yesterday. Why don't you type up into the comments, what do you think the equation of this curve is, with the x and the y? And that's right. It is like yesterday's equation, but there is going to be for the equation of how the center is moving, it's going to have 8 here, 10 minus 2 instead of 10 plus 2. Now notice I don't have any negatives involved because they're both going counterclockwise. Counterclockwise is associated with positive t. But I guess the only real difference here is this. So when it comes to floating, really, whether it's an epicycloid like an epicycloid or like a hypocycloid, if it's not actually rolling, we don't have to worry about some of these extra things. All 5 pieces of information are given to us, namely 1, 2, 3, 4. We need all 5 pieces of information, and they all get worked in. The 2 ends up here, and the clockwise, this clockwise ends up making the t positive, and the other one, sorry, counterclockwise, makes this positive. And this 8 came from 10 minus 2. Okay, now here comes scenario number 2. In this one, it's still the big circle, the small circle, still radius 2 for the small circle, radius 10 for the big circle. But this time, well, we still have the 5 degrees, but this time, while the circle, the small circle, is revolving counterclockwise, that's a little darker than I thought it would be. The circle itself is actually rotating in the opposite, so it's rotating clockwise. So would you write, oh, and I'll show you what this looks like. So the main difference here, on my Desmo sketch, I just have to make one slight change. I just have to come over here, and I think I make this one negative. And now watch. So you see the circle is going counterclockwise, but the circle is rotating clockwise. So it looks like it's rolling, like it has that physics, but it's not actually what happens with rolling, because it's actually going at the wrong speed if it were actually rolling. But you can see I've got counterclockwise for the movement of this little circle, but the movement on the little circle is clockwise. Okay, would you take a minute to write down what you think the equation is for this one? Or how is the equation similar? What changes would have to be made to this equation to turn it into this? So Syed has a couple of minus signs in there. Is that, you are right that there's negatives need to be involved, but is that exactly where the negatives end up going? Okay, good. And Syed fixed it up. The main difference is that the negative sign would go in front of the, because this first equation is for moving around the circle, moving the point on the little circle, whereas the stuff after the plus sign is the movement of the center. Whoops. So this negative sign is like, the main difference that's going on here. That little change makes it so that the point on the circle is rotating clockwise, because it's negative for clockwise and positive for counterclockwise. Now, just to go a little more with this, if I were to take a time where the circle, let's just say the t equals 18. So 18 degrees have happened, so I have this sort of 18-degree angle. That angle is 18 degrees. where will this point end up right now? This is the floating situation. So where is that point on this circle? Where would it have to go? If 18 degrees, if this is 18 degrees, where should I put? I'll make it a different color. So this red, I'll make this point red. This is the second scenario. So where do you think that point should go? I just lost the chat. Yes, Talia, the first one's the direction of the spinning, and the second one's the direction of like the revolution. So where's that red point going to end up? Oh, and I'm sorry, I didn't draw this that well. I had meant to draw it over here. Sorry about that. Okay, so the circle has revolved 18 degrees. That's this angle right here. My question is, where is this red point going to be after this 18 degrees has happened? Where on the circle? Where on this small circle would it have to be? And for an answer, if you could just tell me like what degree mark, like if this is 0 degrees and this is 90 degrees and this is 180, this is 270, or maybe it's not at one of those four places, maybe it's at some other degree. That's right. Ivan says that it's negative 90 degrees or 270 degrees. That is correct. Because if 18 degrees have happened here, and this thing is spinning 1 degree for every, 5 degrees for every one, 18 times 5 is 90. But because as it says it's spinning clockwise, so this point would end up spinning down to here, and it would be at that point. This is going to be really important. Jonah asked about like what's the difference between floating and rolling. Well, the big difference is going to come up as we examine the third question for today. Scenario number 3. Scenario number 3 is an actual hypocycloid. And there's only 3 pieces of information you get. You get the radius of the big circle, you get the radius of the small circle, and you get that the small circle is revolving counterclockwise. That's all you have are those 3 pieces of information. Anyone want to speculate what the equation is? You're not told the rate, and you're not told explicitly whether it's rotating clockwise or counterclockwise. Melissa, do you mean that the small point's going counterclockwise? Because the original point's going counterclockwise. Are they going like in the same direction? The whole circle's going this way. By the way, I'll bring this one up also. For this one, I come over to the sketch that's called rolling hypocycloid. Okay, anyone want to say, based on, you could watch it roll. Notice what's happening to the points on the small circle compared to what's happening to the center of the small circle as it moves around. Okay, yes, Melissa, that's right. So it was the other way around. So what Talia has is the same equation as before. And we're going to see if that could be. It's definitely very similar, but is it exactly the same? So Talia wrote up 2 cosine negative 5t plus 8 cosine t, 2 sine negative 5t plus 8 sine t. But if it's the same exact equation, why isn't it the same graph? So there's something that has to be adjusted about this. And here it comes. Scenario 3. Okay, here's a big picture of it. Now look at what happens at 18 degrees here. This is the same idea as before. I'm going to get that 18 degree t value. So t is 18 degrees, and 5 times 18 is still 90. But unlike before, this is not, this point here, I'll make it red. It's not at the 90 degree mark anymore. How could that be? And what does 90 have to do with this picture? So it's not at 90 anymore, it's somewhere else. But there is a 90 involved in this picture. Where is the right angle? It's not about the opposite direction because it is still spinning. Scenario 2, the point on the circle was going clockwise. When, Joni, you say to the center, 90 degrees, to the center of what? That's right. There is a 90 degree angle, but it goes like that. But when we measure the position on the circle, we don't measure with respect to this line. We measure with respect to this line. And the sneaky trick here is if I draw in one more line, namely this one, this would be 18 degrees also. And that's why this angle here is not, it's not at negative 90 anymore. It's now at negative 72. And that's why, just like yesterday, we need to throw in an extra plus t, just like yesterday. I have some more stuff to show you about that. I have some animation to show you, but this one's going to need a plus t here and here. And it's because when it's floating, I'll show you, I think I could bring this to show you why this plus t has to be there. Well, we could see specifically that it wasn't negative 90 anymore. It was at negative 72. So adding 18 would fix it at least. But let's just see again why that is. Let me compare the floating hypocycloid and I believe that I have down here, if I turn on maybe that point, no, if I turn on this point, I see, I don't think I fixed this as much as I should have, and I'm not able to fix it right now too well, but let's just take a look at what happens. Okay, that's not the point that I want. Sorry, everyone. There is a point somewhere. It's not 10. Maybe it's that. I see. If I could change that to 8, it would be okay. I hope that fixes it. Let's see. No, this is, sorry about that. I'm just going to get rid of this altogether. Let me come back over, let me go to the rolling hypocycloid, see if I can pick up that point. Hmm. Nah, I'm sorry. I did have a really good animation, but I messed it up somewhere along the way. But I'm going to come back over here for a second just to show you again that when it was floating, it was in when something floats, here's like a green point. This point, as this circle floats around, that green point stays 1 unit to the right of the center if it's floating. And that's why when it's 90 degrees, it literally ends up 90 degrees here. That point does not change. It always, that green point stays over here. But when it is rolling, that green point changes. That green point is kind of like when it's rolling, the point that was over here ends up always sort of tangent to the circle. And that's the main difference. That's where the plus t comes from, because the angle on the circle is always in relation to the horizontal line. So this is always 0 degrees, 90, 180, 270. But when I when I actually say like where it is, when I do like cosine of -5t, I need to put the plus t in to account for the fact that this point is moving. So the 5 times 18 is in relation to the green point. But if the green point's moving also, that's where that t comes from. And sorry that I didn't have, what I wanted to show you was an animation where we could actually see that in the rolling situation, the point that's like 2 units to the right of the center of the small circle will always be 2 units to the right in the floating, but in the uh, rolling one, it's like it's tangent to it ends up like if you go from the center through from the center of the big circle through the center of the small circle and then continue till you hit like the tangent point, that would be the where that point ends up. I will fix that up and show you that for next class, but that's the basic idea. Okay, so what's left? Well, there's a challenge question coming. Couple of things. So what causes this to happen? This like cool, because when you did the spirograph, you end up with, Syed asked about the plus t. I think there's a homework question. What if the whole thing is going clockwise? Well, what if the small circle is revolving clockwise instead? That might change it, but they're always going to be opposites of each other. What causes this cool like star thing to go on? When does that happen? Or when doesn't that happen? When does it overlap itself when you go around more than once? Let's say that the small circle is smaller, even if the small circle is always smaller than the rolling circles. Let's keep the rolling circle being smaller than the circle that it's under. But you are right. If the radius, it's not about how big the radius is, and it has a little bit to do with odd and even, but not exactly. So for 10 and 2, and by the way, if I change this last slider here, I can go around more than one time. So here is hypocycloid. Take a look. See, that one is just tracing over the same 5 arcs over and over. What causes, this is where B is 10 and A is 2. It's not really A over B. I mean, it's kind of A over B. Yes, Nicholas. If A is a factor of B, you're going to get repeating. But if you make A like 3, check out what happens. Well, it starts repeating eventually also, but not as much. And if I make it 3.5 maybe, so if it's not a factor of it, you won't get all that repetition, and you get a cool looking thing. And that's why people mess around with the spirograph, and usually the way they make the position of the holes, it's not generally going to repeat, because that would be kind of like a boring thing. Here, I'll make it go around a bunch of times now. So here I have 3.5 for the small and 10 for the big. And you see, as you do it more and more, you get something like that. I think this is Riley's. I picked off some people for homework messing around with a virtual spirograph. So she also used like the football, the track field shaped one. Spirograph. Anyone own this? Or have oh, you do have one. So this toy was made in 1965, and it's got to be one of the great toys of all time. And you still could buy it on Amazon. I mean, $20 if you have like siblings, younger siblings who are at home doing remote learning. I mean, this is a very worthwhile. And there is something about physically doing this thing yourself as opposed to doing it virtually on an app. It's really good. Now, Spirograph, I guess their patent ran out eventually, and now other companies make them. So someone once got me this as a gift, the generic one. Officially, Spirograph, the shapes that are made are actually not hypocycloids, but they are called hypotrochoids. And the official, so this one's called a hypotrochoid art set. And you could imagine, marketing people, maybe someone originally thought that would be a good name for Spirograph. But when Spirograph is a great name, hypotrochoid art set, not so fun anymore. Why isn't it hypocycloid art set? And I want to type in, why can't they call it a hypocycloid art set? What's the difference? Or why are spirographs not hypocycloids, the thing we just learned about? What's the difference between the way you did the spirograph versus the thing we just did? That's right. The fact that the A and B, some A's and B's might be factors of each other, but it has to do with In a hypocycloid, the point that we're tracing is literally on the edge, on the circumference of the rolling circle. But you can't actually put a pen onto the actual edge. There's these little gears, and there's different holes in them. So what a hypotrochoid is like this. You have, this is our last question of the day, you have the rolling circle, just like before, but this time the point that's being traced out is in the interior of the circle. So notice how it makes almost the same thing, but it doesn't actually, it doesn't make it to the edge. So here's the big question of the day. What change do I need to make? Remember, the equation, if this was a hypocycloid, the equation would have been 2 cosine negative 5t plus t, 2 sine negative 5t plus t plus 8 cosine t, plus 8 sine t. This is not the right answer, though. What needs to change? How much stuff so that we can get this picture instead? Okay, have a chat about that. How much stuff would you need to change to create this hypotrochoid? What do you think? Oh, and this time, the you wondering where is this point? It is, instead of being 2 units from the center, it's 1.5 units from the center. So that's going to be relevant. So how many things do you think you need to change now? Have a discussion about that. Type in some stuff. It's a pretty hard question, actually. I'll mute myself while you guys discuss for the next 5 minutes about that. I'll monitor the chats. Just to chime in, there are 3 things that potentially need to be changed. I'd like you to discuss. Do you think all 3 need to be changed? Just 2 need to be changed? Or does 1 need to be changed? You could discuss yellow, green, blue, which needs to be changed, which of them needs to be changed, and if you think they need to be changed, what would the yellow, green, or blue need to be changed to? So take about 5 minutes to talk about that with your neighbors. And this is the last question of the day, so it's a good thought-provoking question. There we go. To help you out with a hint, I have up on the screen it actually happening. So this might adjust what you think. Yellow, blue, yellow, blue, purple. Does this change your mind? Maybe people are chatting. Are people chatting amongst themselves, like privately? Or is really nobody having much to say? So far, I see a couple of ideas that maybe the blue should change to 8.5. Maybe the coefficient in front of the t should be changed to, instead of 5, 10 over 1.5, which is 6 and 2/3. Oh, am I muted still? Can you hear me? Okay, good. Okay, well, we're going to finish out today by getting the answer to this question. But here's your last chance in looking at it to think how many of those three things need to change to get the hypotrochoid, which is the spirograph curve. I could actually change in my thing here. I could change this last thing, which is the offset, to change where. Check this out. You can see how changing it affects the shape. And mine actually lets me break the laws of physics and go outside the whole thing. So that's kind of, weird looking to do that. So that's like the point is outside the circle. That's actually also officially a hypertrochoid. Okay, the finale. Okay, how many people think that, or anyone want to make a defense? If the 2 needs to be changed, what would you change it to? And Jonah asked about the rolling. So 3 things with rolling. Number 1 with rolling, if it's rolling counterclockwise, then the point on it has to be going clockwise, because that's just what happens with physics if you imagine gears. The second thing is that the speed is going to be related to the ratio of the big circle to the small circle, whereas if it's floating, I could just give you any spinning speed I want. And the third thing is that whole plus t that has to happen because of the way that the reference point moves in a rolling circle, whereas in a floating circle, it stays to the right. How many people think the yellow needs to change? And if it does, what should the yellow change into? Okay, Talia says 1.5, and that is correct. And the yellow actually does have to change. The way I think of it is it's almost like a smaller circle that's going around now. And the radius of that smaller circle is 1.5. That's why the 1.5 happens. How about the 8? Does the 8 need to change? Anyone have any opinions about whether or not the 8 needs to be changed to something. Well, if it really was a smaller circle, then it wouldn't be touching the bigger circle anymore, but it's actually not a smaller circle, but it's like there's a small circle on the bigger circle. So the circle that it's still a circle of radius 2 that's rolling around. It's just the point is 1.5 away. So it's in thinking about where on the circle am I, I'm on a circle of radius 1.5, but that circle is on itself on a circle. So Jonas says 7.5. Well, it turns out that the 8 actually does not have to change, because the center of the circle, whether you're thinking of it as the small circle with radius 1.5, or if you're thinking of it as a circle with radius 2, either way, it's the center of the circle is still 8 away from the center of this circle. And now the question of the day: should I change that 5? That 5 was 10 over 2. Should I change to 10 over 1.5? This is the last question of the week. Anyone think that green should change or that it shouldn't change? Okay, and Jonah and Talia say that the green should not change, and they are both right. The green does not change because the circle, even the point on this little circle, it's still going around 5 times as fast because of the circle that it's on. So it has nothing to do with the radius of this little circle. It's the circle that little circle is on. So the 5 does not change. It stays as a 5. And there's only one change that has to be made to make it a hypotrochoid. Just the coefficient of that first thing. Everything else stays the same. So now we have learned how to find the equation for, the spirograph curves, which is, I think, a really good kind of fun application. When you were younger, if you had a spirograph, you had no idea that you were making something that you would one day learn about in parametric equations. And this will probably be, I'll probably start the new unit on Monday, although there are some harder parametric curves, but I probably won't worry about that. I'll probably move on to the new unit. I think over the weekend, I'll put up test number 4, which we'll do the same way as we did before. Let me stop the recording.